Hey everybody, and welcome back to Calc 3 Online. So I want to start off today with just kind of something, two unrelated problems, but just ones that are kind of tricky double integrals. And it's just a lot of times the setup of any higher order integral is always tricky, and these two I think in particular are a little tricky. So it's good practice for harder triple integrals too. But real goal for today is to honestly talk about reversing order of integration for triple integrals, which is much harder, I think, than doing it for two. It's just a lot harder for us to see in 3D how the orders change and all that. So we'll do two examples today and even some more next time too. But yeah, they are definitely trickier problems. All right, so for these two problems, for the first one, I just want to set up this double integral, and I would want you to do it with polar. And then this one, we're going to find the area of the region basically bounded by these, given by these two bounds right here. So for this one, I think it's good to start with trying to figure out what the region is also that we're integrating over. So, when I look at these things, this is x equals this, right? So you have x equals negative square root 10y minus y squared. And then, we could square both sides, get 10y minus y squared there. And then we could complete the square on this thing. So if we do that, we would get this. Remember, when you complete the square, you got to take a negative out because you got to do it with a equals 1. So we basically get, if I move that over, this thing is part of a circle. Whoops, equals 25. So we've basically got a circle that's centered at 0 in the x and then 5 in the y, which I think actually I'm going to give myself a little more room. So it's centered right there, right? And the radius is 5, so it goes here, here, negative 5, 5. So you've got a circle, but if you look at the way this was given, the x integral goes from the negative square root 1 to 0, right? So the negative square root 1 would be this part of the circle. The positive square root 1 would be here, but we don't want that one, so I'm going to get rid of it. So we're going from the negative square root part of this circle, that negative x equals part, over to 0. So we're going from here to here, and the 0 is right there, right? So basically, this is my region that I'm integrating over. And you can see it matches well with this because we're going 0 to 10 in y. So, that's the 10 up there, which is nice. So definitely a polar problem because it's some sort of circular region. And so if I was setting this thing up, I'm just going to go right to polar. So you've got square root of x squared plus y squared. So that's like an r in there. And then you'll have your extra r. So you'll have an r squared dr d theta. And the r is going from, 0 right here out to, this circle, right? And this is one of those that I kind of do want you to just know. The circles that are up, above or below the x-axis are the sine ones, and then they get scaled by their diameter. So basically, if you have, and you could also always get this if you plug in r cos here and r sine here, you'll get the same answer. But the bounds would go in r from 0 to 10 sine theta. So 10 sine theta is the equation of this thing. And then the angle, we don't want 0 to 2 pi, 0 to pi. This is one of those weird things too, where 0 to pi actually gets you the whole thing. You don't need 2 pi. So pi over 2 is here, and then pi is here. So we want pi over 2, right? We want, this angle is my starting angle. So that's pi over 2. And then we want to rotate down to this angle, right, which is pi. So pi over 2 to pi would be what you need. So if you solved that thing out, you would get the correct answer for this thing. All right, so for this one, it's just kind of a cool like double integral area problem, and it's one where really I don't know. I bet there's other ways to do it again, but to me the easiest way to do this thing is just with double integrals. So this is an area problem, right? Because it's a 1. You're integrating double integral with a 1, so it's an area. And I'm going to start off and sort of sketch out some stuff. So we have x equals square root 4 minus y squared there. And so then if you square both sides, x squared, you move the y over, right? You're going to see that you're working off of a circle of radius 2, all right? So you get a circle radius 2. But I don't really need much more of the circle because I can see the y value only goes root 2 to 2, and I'm working with the positive square root. So I was working with like this half, but then I can see that I'm only going to be using root 2 to 2. So the kind of weird thing, though, is that you go the square root thing out to 2, okay? So x equals 2 is this line right here. So right now I'm sort of shading in everything here, all right? I'm going from the circular thing up, or over, I should say, to 2. I'm going to get rid of that, though, because the y is not going to include the whole thing. It's only going root 2, which I'm going to just call that root 2. It's going from root 2 over to, or up, sorry, to 2. So this is my y equals root 2 line. And so we basically have this really weird region where it cuts off here at 2. And then I think I'll just erase some of this in a second. But basically that's the region that I'm looking to find the area of, which is a pretty weird region, definitely. So how are we going to go about doing that? Well, the way I would think about doing this is in 2 kind of chunks. So you can also draw a nice y equals x line right here. And this line, right, would mean that if this is root 2, then this is root 2, right? And what I would actually do is I would get the answer by doing a double integral split up into 2 chunks. One for that part, and then another one for this kind of triangular region right here. So one of those I think is a little easier because the angles are a little easier. And that's actually the red one. So let's just do the red one first here. So this will be a double integral. And I'm going to switch to polar because we get curvy things. And you can see for the r, right, you're going from the circle thing out to this purple line, right? So you go from the circle, which, because of this, the circle will be r is 2, is the equation. So you're going from 2, and then the horizontal line is, y equals 2. Y is r sine theta, so equals 2. So then r is 2 over sine theta, or r is 2 cosecant theta. So we've seen vertical lines, I think, recently, but not horizontal. Vertical are defined by cosecants and, vertical are defined by secant lines, secant thetas, and horizontals in polar are cosecants. So, this is 2 cosecant theta now, right? So we're going from here out to the purple right there. That's R for the red. And then the angle, right, is a little easier, which is why I'm doing this one first. This is right down the middle, right? And we're going from pi over 4 then over to pi over 2. So that's not too bad to see. Pi over 4 to pi over 2. And that's just the red part. All right. Actually, I don't want to use blue because I want to use that for the other part. So we're going to do it in yellow. So pi over 4 to pi over 2. Now for the blue part, so I'm going to have to add to this, right, the double integral of, again, r dr theta. And, you know, in this one, in this blue chunk here, r is going to go from a horizontal line, right, this part right here, the green part, out to the vertical line through 2 there. So we're going to go from like a cosecant, specifically root 2 cosecant theta, and then over kind of like, you know, you're thinking radially out. So you're going from here out to this vertical line, which is 2, and vertical lines are secants. So this vertical line is just going to be 2 secant theta. Okay, so then probably the trickiest part is the angle, right? We need to figure out what that angle is, because that's my lower bound angle. But the way I would do this is it's just trig. So you know that this part is root 2, right? And you know that this part is 2. So you could just say that that angle theta right there, that the tangent, of theta is root 2 over 2, or that arc tangent of root 2 over 2 is theta, right? So we're going to go from inverse tan root 2 over 2 as a lower bound, and then we want this little wedge, so we're going from here over to y equals x, which is going to be a pi over 4 angle. So we're going to go up to pi over 4. I think that problem's cool. But it's one that is actually not too bad to solve. I don't really want to get into solving it right now. I mostly wanted to go through the setting up of that, which I think is the kind of interesting part of that problem. So those are 2 examples, I think, of good ones where it shows you as hard as it possibly could get for double integrals. And, you know, probably today you're also going to see the trickiest kind of stuff with triple integrals now. And that's what I want to talk about right now. So I forgot I wanted to also talk about this really quick. So if we're talking about area with a double integral over here, I thought it was good to talk about volume with a triple integral. And so if I just want to set this one up, I think maybe if there's time, we'll come back and solve it, or I'll just put the answer down at least. So in this one, it's saying you've got these 2 paraboloids. One is like an open up, one's an open down because of the negatives. And so you've got something kind of like this, and you've got x, y, z. This one is a y equals, this one's a y equals, so they're going kind of along this axis. And the orange one, right, is going to be one that sort of just looks like that. And then the green one is going to be going the other way, right, like this. And, you know, it kind of looks like that. And so it's one of these problems, we did one of these before, where basically the shape is like an egg. It's an egg where there's going to be like a middle kind of line that's like the widest right there. And then, you know, it's just kind of this egg structure from there. Kind of like volleyball, or not a volleyball, football. I don't know sports. And so you can do these with triple integrals too, which I just wanted to show really quick. And the way we do it is it's still going to be this weird like integrate one kind of thing. I would do this with just like, I want to do dy first because it's along this direction. And then, doesn't really matter too much, we'll do zx. And if you do set it up correctly here, it truly would be a volume problem, even though it's a triple integral. It's not a four-dimensional volume problem. So you basically just do upper and lower bounds for y, and then so the lower bound is the orange one, which is x squared plus z squared. And then the upper bound is the green one, so 8 minus x squared minus z squared. And then I think for this stuff, I'm just going to do the r thing, because what would really happen is you'd project this graph now, and you're going to get like a circular, like if you do that y integral is what I'm saying, you're going to integrate in this direction first. Then what you're going to get is circular kind of cross sections of this thing. And so what I would basically do with r is I would do a polar double integral. But what I wanted to show you is that once you do this first part, right, you're just going to get a y, and then you're going to plug this in for an upper bound, this for a lower bound. And so you literally get the kind of thing that we've done before, where you just do the upper thing minus the lower function, right? And then you're going to have dz dx. So we've kind of seen this before, because we did some double integral volume problems like this egg one, but we just started here and conceptually talked about why that would make sense. But it comes out naturally from a triple integral also. So I wanted you to see that. But for the sake of time, I don't want to go and solve this. It's honestly not that bad. I will tell you right now, it should equal 16 pi if you want to test it. But that is how that one works with volume for triple integrals. All right, so one of the, I think, hardest things with triple integrals is reversing orders of integration. So just like with double integrals, there's times where this thing right here might just be like a really like easy dy integral, but a really hard dz integral. And so maybe you want to switch those two orders, but then it's going to switch these things, right? So the trick to kind of doing these is to envision what the different projection planes would look like. So like the zy, the xy, and the zx. And then from there, you can kind of start to visualize a different order of integration. So I'm just going to do a dx dz dy here. But first I want to kind of set all these up. So we'll do yz, and we're going to do xy, and we're going to do zx. And basically the trick is look at the bounds, right? So in this first thing, right, z is going from 0 to y, right? And so, in your zy plane, which is probably the easiest one here to do, your z is going from 0 down here up to the line, z equals y, which is just going to be this line. And so you're just going to get this kind of thing, and it's going to eventually get cut off over there. We'll talk about that in a second. But that's kind of what it would look like in zy. In the yx one, right? So y is running from 0 to x squared, right? And x runs 0 to 1. So the way I kind of think about this one, I guess, is if x is running between here and y is going between these two, right? X squared is going to be, positive, right? So, it's somewhere, it's fair to say that that's less than or equal to x, right? Which is less than or equal to 1. So if you look at what this is saying, basically y is less than or equal to x squared, right? So here's my x squared, but it's also less than 1. So, it's not going on forever. Eventually you get to 1, and it cuts it off. And it's also saying x is less than or equal to 1. So you basically are getting cut off there too. So you're getting this region in the xy plane, just based on really looking at this bound and this bound. Then the last one, you kind of have to pull in the first bound again. So remember in the first bound we're saying that z is equal to y. But we also knew all that stuff that like y was less than or equal to like x squared. So that means also that, what I'm saying there is z is less than or equal to x squared. So in this plane, right, here's my, part of my z equals x squared. I know that z is less than that, but I also know that x, only goes 0 to 1. So I get these nice cutoffs again. So here's 1, here's 1. So I'm getting that. So this is truly x squared. This is x squared. Maybe I should also add equals y equals z. And this one is y equals x. So those are really what the different regions would look like in the different projections. And so from those, you can kind of use those to answer these questions. So we're just going to put f of x, y, z. And I want dx, dz, dy. One thing, you can see that no matter if you're in x, y, or z, right, you always go 0 to 1. So a lot of times the outer integral is like the easiest one to do. So that one definitely is, and it's got to be a constant, right? So it's 0 to 1. That one's not too bad to see. The other ones are not as easy. For dx, right, way I kind of do this one is I look at anything with the x's, and I just kind of look at what the lower bounds look like, right? That has no x's, so that one's not that helpful to me right now. Oops, I just wrote x up here. Should be z. So you can see in both of these, right, the lower bound is the curve, the x squared part, right? So I can, if I take like this one, if I solve for x, right, which is what I need to get this to be an x equals and this to be an x equals thing, I can see that square root of y running up to x equals 1 would work, right? Square root of y up to 1. Then z, you kind of do the same thing. You look at, the only thing you got to be careful of is the bounds here cannot have x's in them, right? Because the only thing left over is y, so you can put y's in here. So if you look up here, right, you can see that z goes 0 up to y. So that would be basically how I could use that one to put in the bounds. And if you did that integral out, it truly would be the same thing as this integral. So I recognize these things are pretty tough, so I want to do one more of these. And definitely a little bit harder, because what I want to do here is kind of, based on these bounds for this is like the object kind of that we're integrating over. I want to rewrite this integral in the other 5 orders, right? So basically normally, right, you have 3 times 2 times 1 orders. We got 1 right here. I want the other 5. So same kind of thing. I'm going to try and draw what the projections look like in the different regions. And I think to me, the easiest one to see is honestly, like, you can sort of see the projection already in the back here for this triangle, right? So in the YZ plane, it's just going to be a triangle, right, with the bounds 0, 1 in both directions there. So 1, 1, diagonal line, there you go. And this is like literally y equals, whoops, y equals z. Some of the other ones, actually another one too that's not so bad, right, is down here. You can see this one perfectly fine. So that's the y equals x1. So you've got to kind of flip your mindset there with it, I guess. But I think I can do better than that. So we're going to say it's like that. So y goes up to 1. And then it's this kind of region in there. And this is also 1, right? Because I guess the reason it's also 1 is there's this line or this curve right here, right? Which is given kind of by that down in the y equals x plane. And so if you just do y equals square root of 1, right? You get 1, and so x has to be 1 also right here. So here, let me clean up some of this. So then the only other one you have to deal with is the one where you push it over into the xz plane. If I kind of bring this one, I guess, back a little bit, you can kind of see that, there's going to be a curve in the plane, right? If you push this over, you can see that it's going to kind of curve up and towards the z axis right there, right? So like in this direction, it would be curving like that. So if I push that one over, you project this over, right? You're going to get like this kind of shape over in that plane. So much red there. Okay, so still a 1, but now we're kind of curving like down like this. And so that's a pretty bad curve. I have to try that again. So it's more like that. So that's kind of what it'll look like. Okay, so those are my projections. And the nice thing is that all these, right, bounds go 0, 1, 0, 1 on the respective axes and stuff. So when you do the other 5 orders of integration, they always end in 0, 1. So I'm going to get that set up right now. So another nice thing here too is if you start the same way, so like there's another dz one, right? dz dxy instead. Then you can just keep the same bounds, right? There's no reason to change it if they start the same way. So I would just keep this one as 0, 1 minus y. And then you just need to look at xy, right, over here and switch it around, right? So in that case, so I put the equations here. So we needed these equations, right, which you can just get out of, if y is square root of x, then x is y squared. And so I need x equals things here, right? So x goes 0 up to the curve, right, which is y squared. So that one goes 0 y squared. We got 1 done. And then for like the dx here, we definitely, if we look at this picture, we go from 0 in the back out to this curve here, right, as we come out. And so we go 0 out to that curve, but that curve written as an x equals instead of a y. So it would be y squared, which means that this bound is also 0 and y squared. And then for y here, you have yz left over, so you should look here. And I just realized that looks wrong. That's not y equals x. That is, there we go. So it's either 1 minus z equals y right there, or you could flip things around and do 1 minus z equals y. So the y bounds there would be that, because we're going from here out to this line written as a y equals. And kind of likewise, this one would be 0 out to 1 minus y, right? There we go. For the same reasons. We're just going a different direction, right? 0 up to 1 minus y. All right, and I'm running out of time very fast here, so I put the answers for the other ones up, and we can talk about those some more. But you basically just keep going through these pictures, and sometimes you do have to do some substitutions to make it work out nice. But we will talk about these in class.